Okay, welcome. Now we're going to do lab 4. Okay, now lab 4, which looks like this, and you should have read it, you'll note, is involving springs. Okay, so we're dealing with forces and springs. Now the Hooke's law. Okay, this experiment comes in a couple parts. The first part is we have to determine K. So I'm going to show you how we do this, all right? Then I'll do a demonstration. So we're going to plot, if you read the experiment, you'll see what it says. We're going to plot the force here and X here. Okay, now the force is really the weight, which is in mass times gravity, which is in newtons, okay? The X is really a delta X. Because if our spring starts at a 0 point of 30 centimeters, which is what we'll get for this one, when you first load it, it stretches to 37. So the displacement would be 7, not 37. Okay? So it's a delta X. And we'll do that in meters. Okay? So the reason we're going to deal with newtons and meters is those are our standard SI units, even though we're going to measure centimeters, we're going to measure grams, but we'll convert everything to newtons and meters. That is a common error in this experiment where students fail to do that. Okay, so what we're going to end up doing is we're going to start out with 0, which is with no weight on it. So it's relaxed. 0 mass, 0, and 0. Now that happens to occur at 30, so we're going to say X minus the 30 centimeters will be 0. Okay. Now the first thing we're going to do is add a mass to it. So let's just arbitrarily say I put 50 grams here, and I got 37. 37 minus 30, this is really 7 centimeters. Okay, and I'll plot that point. Then I'm going to plot another point with some addition. So let's say that's 100. Okay, and we're out to maybe 42. Okay, so then we're going to plot another one, and so forth until we have several of these plotted. Now you've done this kind of analysis before. You did it in lab experiment number 1, and you probably have done this a couple times through the course. But at any rate, we're going to do a regression analysis, and that's going to give us something that says y equals mx plus b. Okay, now that I've got the line, I know the intercept is 0, so I can get rid of that. And if this is force equals some constant, we'll call it k, times x, I now have Hooke's law. So the slope, which you know is m, which is force over x, Hooke's law, I'll write this in different colors so you can see a little easier. Hooke's law, F equals kx, F over x equals k. So therefore, the slope of that line is a spring constant. Okay? That's how you do this. You're going to have to plot data, and you're going to have to establish that line. You're going to have to plot that line, and then you're going to have to calculate K. And that's about it for the first part of the experiment. Okay, I'm done. All right, so here we are back to part 2 of this experiment. Now we've already determined K. And if you think back to how we've conducted all these other experiments, K is now a control variable. Doesn't change. We're using the same exact spring. Okay, and I actually put another spring up here so that it would be a little bit different. But first we're going to determine K, then we're going to go into, wipe this out. I jumped into part 2, we're in part 1. All right, so now we're back to this experiment. I just showed you the math on how to determine K. We need K because that's going to be a control variable for this experiment. What that means is we have all the same height, we have the same exact spring, and K doesn't change. So the control variables for this experiment are pretty simple. Just the length of the spring unloaded, and then K is the inherent return of the spring. I put a second spring up here just to show you how different these are. There's one that if I let go, it oscillates, and this one doesn't oscillate much at all. So you can see the difference, and that's obviously it would be subtle if this was a different spring, but it's the same kind of a notion. Now, what I'm going to do is first thing I have to do is measure the bottom of this unloaded spring. That's X0, okay, X0. It's the 0 point on the spring with no load on it, okay? Now, it may be X1. If I put no load on it and say measure X1, X1 minus X0 is still 0. So if I look at this thing, when I measure it from the top down to here, it's about 30 centimeters, okay? So that's what we're going to call it. We'll call it 30 centimeters, all right? So 30, there you go. Okay, so it's 30 centimeters. Now, when I lower, let's put the first mass on was 50, okay? So I'm going to put a 50 on it, and it only stretched a little bit, didn't stretch very much at all, okay? Now I'm going to put, let's not put the 50, let's put 100 on to begin with, okay? So we're going to put 100 on, and again, it only stretches a little bit. Now I'm going to put an additional 200 on, or a 200, which is an additional 100. So there's 200, okay? Now notice I got a motion out of that. So the range I really want to use on this is when I see that I've got some kind of a response from the spring. So there's a 200, and I can measure the bottom of this thing and whatever it is. I'm going to give you data, but this turns out to be about 35 centimeters or so. For this spring, you're going to get a different spring, but I'm just showing you the technique. Now I'm going to throw another weight on there. There's 300, okay? Now if I take the 300 off and I put a 400 on, that's a 200 and a 200. There's a 400. Now, go back to the data, we would have to measure each one of these, okay? So this particular one is probably reading, I don't know, 45 maybe. Okay, so I can plot the responses for each one of these as I add more mass to it. Remember, adding mass is the same as changing the weight or adding force, okay? So, because gravity is constant. So now I've got some responses to this thing for several masses, and I can plot those, and I can determine a value for K, all right? That's the end of part one, and it's really important that you do this carefully to get K, because you're going to need K for every other calculation in the experiment. It's a control variable, so just remember that, okay? So we'll just turn. Okay, welcome back. Part two of the experiment. Now, I'm going to try and explain this very carefully because this is a common source of error with students. So the first thing I'm going to do is draw a spring. It's got no load on it. So we're going to call this Y0. Okay? Everybody's got that. Now, when I add a weight to it, draw the next one over here, okay? It gets down to some point right here where I can call this Y1, okay? Or if you prefer, we'll call it Y final, or we'll call it Y2. It doesn't matter, it's Y1. And So we've added some force to this thing, and we stretched it some y1. Okay. Now we know that Hooke's law applies. F equals kx. So the x, or the delta, is always y1, some y measurement. Let's just call that y prime. Okay, just let's call it yn, because we're going to do a couple of these, minus y0. Okay, so this thing actually stretched y1 minus y0. Okay, now if I add an additional weight to this, okay, I'm going to do this in red here. So we can say here was the first y1. Now I added more weight to it. And now I'm down to here. Okay, we'll call that y2. Except I'm measuring everything from y0, so it's y2 minus y0. So the change in potential energy from y1 to y2 is 1/2 k y2 minus y0 squared minus y1 minus y0 squared. Do not forget to baseline everything to y0. That's all I'm going to say on that. And we'll figure, oh, this is, let me call this U, potential energy. Okay? So that's all we got to do for this part of the experiment is we're going to take some measurements as we add some additional weights. And that's all I've got. Okay, now I'm going to demonstrate this part 2. We just talked about it a little bit, but you need to pay some attention here for a second. I changed springs just because this spring gives you a good perspective on things. Right here is the y0 height. Okay, we can measure that. In the experiment, they call that y1. So you could say y1 minus y0 is 0 right here. Okay. Don't get hung up on the subscripts. We have a starting point and a final point somewhere down below here. Okay, we're taking the height from the start to the bottom is a change in gravitational potential energy. Now you know this, so we can say that potential energy gravity equals m, whatever the mass is, GH. The difference. The H is going to be this Y final minus this Y initial. Okay, that's gravitational potential energy. And if you think about it, when you're holding this thing up here and it's not moving, it's got 0 kinetic energy. When you let go of it, kinetic energy picks up until it gets down to the bottom, when all of the gravitational potential energy is now spring potential energy, because just as it gets to the bottom, stopped its downward velocity, kinetic energy goes to 0. So I'm going to demonstrate one of these just by, and let go of it, and watch very carefully where this goes, and it comes back up, okay? So when it gets to the very bottom, remember it has no kinetic energy, it's all spring potential. So this is an example of us changing kinetic energy, 0 kinetic energy and all gravitational potential energy, dropping it down. It's got kinetic, now it slows down. No kinetic, but all spring potential, and then coming back up. That's what we're going to try and measure. So I'll give you the data when we do it, and it's not the same as this spring, but we would essentially start with our spring length is at 30, okay, happens to be where I put it, and I will drop this thing. So I'm going to hold it at 30, is what the experiment says. Hold it at 30. I'm measuring to the bottom of the spring, not the weight, and I'm going to let it drop, and I need a good set of eyeballs to measure that. but this ended up going down to about 57, okay, give or take. I'm not real precise on this just yet. Okay, so we could say it started at 30, it went to 57. MGH, H is 57 minus 30. Then we have 1/2 kx squared, or 1/2 k, the initial is 30. We'll call that 0, 30 minus 30. And this is 57 minus 30. So 57 minus 30 squared minus 30 minus 30 squared gives me the potential energy. And this experiment, you'll know you got it right if the numbers come out close, because it's very accurate. It predicts very well. And the biggest mistake is people forget that you're starting at 30 and everything has to be measured from 30. So the stretch of the spring is 57 minus 30 for X2 on the spring. X1 on the spring was 30 minus 30. The gravitational spread is 57 minus 30. And that's all I want to say on this experiment.